Shall we start now?
Yes, we can start.
Good evening, everybody. I welcome our resource person and all of you to this last session of our workshop. Over to Professor Vishnu Gambati, our beloved resource person.
Thank you very much, ma'am. So we are entering into the 15th day of the workshop and the last day of this series of lectures. So till yesterday, I think we have covered almost all the basic topics, and not just basic, somewhat advanced topic also in Python programming, especially scientific programming using Python. Scientific in the sense that we have used many of the modules like numeric Python, scientific Python, matplotlib, symbolic Python, all these things. So yesterday we were discussing something related to Gaussian elimination for a solving system of equations. So after discussing that, now it's time for discussing another type of method for finding solutions for system of equations, which is known as LU decomposition method. So in the LU decomposition method, what we actually do is we given a matrix A, the coefficient matrix of for a corresponding to a system of equations. Given a matrix A, we try to decompose that A into a lower triangular matrix into an upper triangular matrix. Lower triangular matrix, we know that it's above the main diagonal, everything is going to be zero, and upper triangular matrix below the main diagonal, everything is going to be equal to zero. So once you are able to split that A into upper triangular, lower triangular, and upper triangular product of that, we will be able to solve system of equations much more easily. I will start sharing a PDF textbook which actually explains the theory behind that so that we can understand what exactly is happening. So how exactly to achieve is what we are going to do in the programming. Why we are doing all these things is given in that particular textbook. It's scientific programming using Python. That's the name of the textbook. Not scientific programming, I think numerical analysis using Python. So let me start sharing that screen first. So from this, we can easily understand that why we are doing all these things and what is the logic behind doing all these decompositions. So the textbook is here. So essentially, what we are trying to do is um, a square matrix. We are going to express it as A is equal to LU. Okay, that's what we are basically trying to do. So suppose that we are able to we are succeeding in decomposing this into product of the form LU. Okay. So suppose now that we have to solve the system of equations Ax is equal to b, where x is the variable matrix. X is the matrix consisting of if it's 3 by 3, that x is nothing but x, y, z. Okay. So we have the system of equations to solve Ax equal to b, where A is a square matrix. Now, suppose that we are able to factorize this A into L union L into U, where L is a lower triangular matrix and U is an upper triangular matrix. So we have LU is equal to B. After this, writing this LUX is equal to B, just take this ux is equal to y. Okay, so x is known to us. X is nothing but y1. Sorry, x, y, z. This variable matrix x is nothing but it's a column matrix consisting of the variables x, y, z or a, b, c. Okay, depending upon your the system, that symbol you are using in the system of equations, we can take it to be equal to a, b, c. It's a column matrix a, b, c. Now, suppose that we write ux equal to y. Okay, so we don't know what exactly. We know that u is also a 3 by 3 matrix. X is a 3 by 1 matrix. So u into x is going to be a 3 by 1 matrix, which is a column matrix. Okay. So whatever we are getting, call this to be equal to y. Suppose that this is y. This is a column matrix and call this as y. Okay, if this is we rename this to be equal to y, so essentially the lux equal to b becomes ly is equal to b because this is equal to y. So it becomes ly is equal to b. Remember that this y consists of combinations of a and b, a, b, and c. Okay. So ly is equal to b. In this y, there are certain expressions which is a column matrix. Now b is a constant matrix we know. L is a lower triangular matrix which we already have found. Now solving a lower triangular matrix into y is equal to b, that's possible, so that you can find out this y exactly. Because solving a lower triangular matrix is easy. That's basically because lower triangular matrix we know that the only one element is there on the first row, which is the very first element. Other than that, everything else is going to be equal to 0. So you can easily find out that particular element. For example, suppose that it is equal to 2. Suppose that you have some entry y1. So 2y1 is equal to the corresponding entry in b. So you can solve for this y1 therefore. Okay. So you will be able to get this matrix y, column matrix y. You can completely get this column matrix y. If you are completely getting this column matrix y, then you can easily solve this ux equal to y. Once you found the values of y, you can solve this ux equal to y because u is now an upper triangular matrix. Okay, once you see the example, you will be able to understand it properly. I'm just saying so that you will get a feel of what exactly we are trying to do. So now we can solve ux equal to y for x because y is already known. You need to find x, but x is what we are supposed to solve in the beginning. We were supposed to solve in the beginning. So the complete system is therefore solved. Therefore, the entire thing that we have to do here is to split this A into a lower triangular matrix into an upper triangular matrix. Okay, so we will try to see the full example. Okay, now how do we split this lower triangular into upper triangular? Assuming that it's possible to split A as L into U. So if it's an upper triangular matrix, okay, in this particular case, we are assuming that in L, the diagonal row is nothing but 1, 1, 1. Okay, diagonal row is 1, 1, 1. Main diagonal consists of 1, 1, 1. And below that, there are some entries being lower triangular L21, L31, L32. And U is the upper triangular matrix U11, U12, U13, 0, U22, U23, U33. Okay, this is the kind of split up we want. If A is equal to LU, then naturally what happens is that we know that A, the coefficient matrix, is known to us. Okay. If you multiply this L and U, what happens is we get U11 because this part, the upper triangular part of L is nothing but it corresponds to the identity matrix. So if you multiply, you will get 1, 0, 0 into U11, 0, 0. So you will get U11. So correspondingly, if you multiply this L and U, we will be getting U11, U12, U13. U11, L21, U12, L21, U2 plus U22 like this. This is the product. So we are simply multiplying this, assuming the existence of an LU decomposition. Fine. Now, remember that we don't know what is L21, L31, L32, what is U11, U12, U13, etc. These things are not known to us. Now, what we are trying to do is we are going to apply Gaussian elimination. We are going to use the method of Gaussian elimination so that only U11 will be remaining in this column as non-zero, possibly non-zero. And so how do you make sure that the entry in the second and third rows corresponding to U11 below U11 is equal to 0? You need to apply row operations. But what is a row operation? You need to multiply the first row with L21. You need to multiply the first row with L21. Okay, and second row should become row 2 minus L21 into row 1. This is what basically you need. Fine. So this is very important. Row 2 is L21 into row 1. So in effect, you have actually subtracted. See that U11 is known to you. U11 is quite clear to you. Now, second entry is U11 into L21. You are using that L21. So you can subtract row 2. You can take the difference, row 2 minus L21 in row 1. So you need to just keep remembering this what this L21 is. L21 is needed. Okay. We will push this L21 to a matrix. Similarly, we get L31 also from this. So A is clearly known to us, right? A is known to us, therefore U11 is known to us, U11, L21 is known to us. If these two things are known to us and U11 is known, from this we can get L21. Similarly, we can get L31 also. Once you find this L21 and L31, you can make these operations. So finally, you will be getting A is equal to, after these two operations, you will be getting a matrix of the form U11 0 0 below that, and see that the second row is completely changed to U22 and U23, just that. The way in which we have taken L and U, what happens is that only U22 is left here and U23 is left here. So now we are going to manage the second row. So how do we manage? What are we going to do with the second row? We want to make this U12 and U22 L2 L3 to 0. So for that, sorry, that is not actually necessary. See, we want to make a lower triangular matrix. So sorry, upper triangular matrix. So we want to make the second element in the third row to be equal to 0. So that again apply the row operation. Row 3 becomes L32 into row 2. Row 3 minus L32 into row 2. So after this operation, what happens is this much is left. So U is now here, an upper triangular matrix. But remember that while doing all these things, we have actually computed L32, L21, L31. But these are the only 3 elements that we have to find out in L. So while computing the upper triangular matrix, we have actually computed the corresponding lower triangular matrix also. So we have L, U both with us. We have L, U both these things with us. Okay, so finally, the only thing we have to do is we have to find this U, and during that course, we will be finding and saving this L21, L31, etc. into another matrix. That will be the L matrix. Now let us see how to do all these things. But after that, we will see how to get this, how to solve the system of equations correspondingly after doing all these things. We'll come back to this textbook. After finding the LU decomposition, we will again come back. Okay, let me take one example. I don't know, some example is given here. Let me just see. No example seems to be here. I will find out an example, and we'll start with an example. We'll start with that example. Maybe we can start with yesterday's example itself, because yesterday itself we have done something. We had one program. Maybe we can make use of that very program here. Not this one. It's with 0 0. Maybe the program even before that. Okay, let me anyway. I will be copying and pasting one matrix from yesterday's programming. So I'm keeping the name as 64 LU decomposition.py as the file name. So the very first thing we have to do is we need to define the matrix A. Okay, let us start defining the matrix A, and after that we will try to do all these operations and save this U21, U21, U22, etc. need not be saved, because after all these kinds of Gaussian elimination operations, we will be getting the final matrix as U. The only thing is that in between, you need to save the variables which you are multiplying to different rows for performing the Gaussian elimination, and that those particular numbers are going to constitute the L matrix for us. Okay, let me take yesterday's matrix. Maybe I can open it from here. So Gaussian elimination. Yeah, the matrix is here, so that we can compare also. So the matrix is here. Let me save it. Okay, I need to start. Sorry, I have not started the spider window for you. Let me just do that. Here is the spider window. So the matrix is here for us. Now, what are the steps that we need to perform? Remember that we need the decomposition of the form A is equal to LU, or AB is not required, just A is required. So we need to delete B. We can probably use later. Maybe even we can write this B here itself. So only the last thing is required. Maybe we can even define it as a column matrix and row matrix and then transpose it. I don't know whether you need NP transpose. I'm not very sure about that. Okay, we just see print B. Okay, NP is not import by us NP. Oh, that's fine. So we can just take the column. We can just take the row matrix and take the transpose of that, so that it will become equal to B. So B is the constant matrix, and we have A 4 2. Oh, sorry, that is not deleted. So we are just taking A, only the coefficient matrix. So A is here, B is also here. Now, what is the first thing that we need to do? Finally, we are going to get an upper triangular matrix, right? So the second row, first element, we need to make it to 0. So how do we do that? So second row we should manipulate. You see that in the previously we tried exactly the same thing. Not this one. 63 is general. So 62 was the the method where we tried concretely something. Yeah, it's here. So this is what we are going to try now. So this is the operation that we want to perform. Okay, so previously we multiplied it with 1 by AB. That's not really necessary. So instead of that, so the first thing that we need to do is row 2 we are going to multiply it with. Now we need to remember that using which element we are multiplying, we need to remember. See that we want this minus 2. We want this minus 2 to be, so we want this to be equal to 0. We want to make this to be equal to, so 1, 1, 1. Okay. This minus 2 we want to make it to 0, so that for that thing what do we need to do? So we need to multiply this with some element. This with which element we have to see. We need to multiply this row with some element and add it to this particular row. So that is row 2 should become row 2 plus some number. That number is nothing but that is going to be L21 for us. Row 2 plus L21 times, this is what we want, L21 times row 1. So which number we need to multiply? That's the first thing that we have to check. Using which number we need to multiply. See that we are assuming, at least for the time being, that the entry, the first row, first element is going to be equal to non-zero. That we are assuming, because if it's 0, there is nothing to do. If it's already 0, there is no need of doing anything. So if it is 0, we will simply skip that step. Otherwise, what do we need is we need to multiply this with what? See, we wanted to add row 2 plus L21 times row 1, so that this element becomes 0. So how do we locate? How do we find that element? With what we need to multiply? So see, previously what we did is that we converted this row into we entirely converted this row by taking 4 outside. We multiplied with 1 by 4. After multiplying it with 1 by 4, we added this minus 2 with that. So instead of that, we can multiply with the minus 2 by 4, right? We can multiply with minus 2 by 4. So that 4 will be cancelling and minus 2 will be adding. Therefore, minus 2 by 4 is what we actually require here. So L21 is nothing but we need to take it as minus L21. Okay, we need to save it as a matrix. For the time being, let us just keep it like that. After that, we will push it to a matrix. L21 is nothing but what is the first element? How do we call the first element? This AB is wrong. This should be A actually. Here also. Okay, we'll make those changes later. L21 is nothing but, so you need to divide the first row with 4 and multiply it with minus 2 and then add to it. So divide with 4, multiply with minus 2. Therefore, minus 2 by 4. Minus 2 by 4 is nothing but it is the first entry in this second row, minus 2. 4 is the first entry in the first row. Okay, so how do we access these elements? A, the first minus 2 is nothing but 1, 0. divided by assuming it to be non-zero, of course. We need to check if it's non-zero or not. That's our initial job. Let us take care of that thing later. A10 divided by A00. And we need to add. Okay, so according to the description of according to the way in which we are solving, we need to add or we need to subtract. I think subtraction is better, because adding means that we need to again multiply it with the minus one. So if you're adding, then it means that multiplying with minus 2 and adding will not work. Therefore, you need to take a minus also. Okay, you need to take a minus one also. Minus. So let us see what happens after this. So the first row is going to be modified. How do you modify the first row? First row is going to be, so you need row 2 becomes, what is row 2? Row 2 is nothing but row 2 is this. Row 2 becomes row 2 plus what times? L21 times. Not plus, actually it is minus. L21 times. So subtract it. Similarly, this becomes L21 times. Okay, what do we mean? Here it is not L21 actually. Here you need to find L31, not L21, but L31 is required. So find L31. How do you find L31? L31 is nothing but A10, not A10, A20, A20 by A0. So exactly the same procedure. So this becomes L31 A of this. This is the first one. This is the second transformation. This is L31 and everything else is exactly the same. Let us see it in action and see what is the result after this. Okay, what is the value of this? Print L21. L21 is 0.5. So I need to multiply this with 4. Sorry, I need to multiply this with 1 by 4. 1 by 4. Therefore, this becomes 1. And multiply with minus 2. Did I do exactly the same thing? Multiply with 1 by 4. That's fine. That's correct. Multiplied with 1 by 4. That's fine. After that, what did I do? Oh, am I using everywhere exactly the same? A1 becomes minus L21. Already there is a minus, I think. Okay, that's the problem for me. Already there is a minus. So we already have a minus there. No, this is not required. And here, according to what we have seen, here minus is required. Here minus is not. Okay, that's fine. See this? So you are getting the first column in that upper triangular matrix is now fine. So instead of pushing it like this, maybe we can take this. We can suppose that we know that the lower triangular matrix is actually the main diagonal corresponds to the identity matrix. Okay, so we can initialize this L2 consists of the identity matrix first. After that, we can keep on modifying the entries appearing below the main diagonal. So let us take L initially to be the identity matrix itself. L equal to np dot identity I think 3. Let us see it in action if it's correct or not. Okay, this is fine. Now which element we need to change? L21. L21 is nothing but, okay, 1 less. So L10 we need to change. L10 we need to change, and correspondingly here we require it was L31, so L20. This is what we require. So let us change the elements even here. L21 changed, so that we can get the final matrix simultaneously. Let us see this L also now. Printing A, not actually A, this is transformed one. See that L now has become 1 on the main diagonal, minus 0.5, 0.25 here. We are not completed. Only the first step is over, because the upper triangular matrix is not complete. The upper triangular matrix is only up to here now. So 4, 0, 0. So to make it upper triangular, remember that we need to remove this minus 1.5 and 3.75 also. Okay, minus 1.5 and 3.75 also needs to be removed. So going to the next step. So how do we go to the next step? Same kind of procedure we need to adopt. So now here we need to, so this element we are going to find now. Okay, this element we need to find. So for find, remember that this element is not necessary to find, because this is already 1. We are not going to change this. So for determining the log triangular matrix, we require this element, this one, and this one, 3 elements. Now this one may again change, because we are going to apply again some change. So it's possible that this may change. Okay, since we are applying some change here, transformation here, this also may change. Now this is our A. Transformed A is here. L is here. Okay, both these matrices are here, and L is also here. So I think A dot shape, will it work? No, that's not. Shape is just giving, no, it is not like that. Okay, let us just remove that. Okay, so this matrix is here now. Now what is the next thing that we need to do? We need to just change. Okay, let us just push it to the next row, next line. So here we want the other change, and here we don't have to change, because we need only an upper triangular matrix. So this is not entirely like the Gaussian elimination, where we try to remove that leading element, the leading non-zero element above and below. We try to make 0 in the Gaussian elimination, but here we are not going to do that. Okay, here we are just trying to do that. What we are trying to do is that below this we want only an upper triangular matrix, so we will simply remove this minus 1.5. That's only our that's the only aim that we have. Okay. Now we are going to repeat exactly the same procedure. We need to find out. So next element is L32. Is it L32? L30? L31. Okay. Next element we require is L31. We want to manipulate L31. Sorry, L31, not L31. L31 according to our usual matrix notation, it is not, it's L32 actually. This is L32, not this one. Okay, here from here we will be finding L32, but according to our notation, we will be calling it as 3 to 1 less. Therefore, L21. Okay, don't get confused with that. I myself getting confused sometimes with that. So the notation here, the counting here starts from 0. Therefore, we need to reduce both the indices by 1. So though we have to determine L32, we will be writing it as L21. So L21. How do we find L21? So the aim of finding L21 is that when we are adding a number times this to this, not adding, subtracting. In fact, so the row 3, now the transformation should be actually on row 3. Okay, let us just type that first. Row 3 should become row 3 plus. So what is required? Row 3 not plus, row 3 minus is what we are writing here, minus. So minus. There can be a change of plus or minus symbols. I think otherwise there should not be any difference if you use plus or minus. So L21 equal to, so we require, we need to see, we need to make this this 3 as 1. Therefore divide it with A what is this entry? This is A22 actually, but we should call it as A11. Okay, so divide with A11, A11, and multiply with this entry. This entry is nothing but A. This is A32, but instead of A32, we have to call it as A21. A21. So that entry is also here. Now the row operation. What is the row operation? The row operation is here. So the third row should become L21. Third row minus third row becomes third row minus L21 times, not the first row but the second row. So let us see both A and B. Remember that A is actually becoming upper triangle. So that is actually one thing we should remember, that we are actually losing A. So I think it's better to just copy this into some U and start transforming, because otherwise after the end, at the end of the program we don't have A anymore with us. We have only U and N. Four minus 2 1, 0 3 minus 1.5, 0 0 3, 1 0 0 minus 0.5. This is upper triangular. Sorry, this is lower triangular with ones on the main diagonal, and 0.25 minus 0.5 etc. on the below diagonal. Okay, if you want to see if it's actually giving A, if whatever we have done is correct or not, we can just try to multiply these two. Print np dot. Let's multiply A and L and see. Oh, sorry, L and A instead. Is this the same matrix? Yeah, this is 4.0. Okay, this is 4.0 minus 2, 1, minus 2, 4, minus 2, 1, minus 2, 4. Exactly the same matrix. So that LU decomposition is complete now. So as I told, we need to probably change this A2. Maybe we should keep this as some U, and we should try to, because we are transforming this A to become finally an upper triangular matrix. So towards the end of the program, we don't have A anymore with us. That's the problem. So maybe we can call this as U equal to A, and transform uses A everywhere, uses U everywhere instead of this. U, U, oh, sorry. Right. It's U, here also U, so that we can finally show once again what it says. U is this, U is this, U is this. Maybe we can even, in the final step, print A, or otherwise use formatting, print star U, or otherwise equal to formatting L here, U here, and maybe L star. Oh, sorry, L star U we should not use. So if you use L star U, it's actually that the term by term multiplication is happening. Is it happening correctly? But the formatting is not probably proper here. Maybe we can. So this is the upper triangular U. This is L. U is here. Oh, what's happening here? U. Okay, somewhere here. Sorry, gone down. So U is here, 100, etc. But this is wrong. What is this? Maybe I am printing it too many times. Okay, otherwise, let me just remove this and try. U is this, L is this. Okay, this is fine. Something else is happening. Okay, let me just update the Google document with this. Yeah, the Google document is updated. So the essential thing that we need to check is if this U10 is already 0. So what do we do then? As in the previous case, we may have to bring whatever. If the first entry, if the first column is completely 0, then we cannot do any of these things. Okay, if the first column is completely 0, then okay, then that U entry will be just equal to 0. In that case, we don't have to do anything. Just probably leave it like that. Let us try to see an example like that. Right. So this is how we perform the LU decomposition. Now, the next thing that we have to do is we need to solve the equation, right? We need to solve the system of equations. Suppose that we have the system of equations. Let me just take an example. We have already have this example. Okay. So previously we had a B also here. What is this B? So we have the system of 4A minus 2B. So the system we have is 4A or otherwise 4x plus minus 2y. This is the system we have, plus 4 2 minus 2 1 set equal to, what is our B? B is this, equal to 11. And next equation is, oh sorry, this is the first. Okay, 1 4 into minus 2 into 1 into, that's correct. So next is minus 2 x plus 4y minus 2z equal to the second entry, which is minus 16. This is equal to minus 16. The next entry is the last one, x minus 2y plus 4z equal to 70. So this is the system that we are trying to solve. So the next thing we need to do is, so we have now L is there with us, U is also there with us. Okay, so okay, let me just comment this out so that otherwise the program won't work. So once we have found out this L and U, the next step is to take actually, according to what we have seen now, what we have just now seen. So we need to take Ux is equal to Y. Okay, so Ux equal to Y. Remember that our initial system is Ax equal to B. Ax equal to B. Now we are trying to put Ux equal to Y. Okay. Assuming that Ux is equal to Y, Ux is definitely going to be equal to some Y, definitely. Okay. So what is this Ux in our case? Maybe we can use symbols and try to multiply. Okay, and try to see. So X can be taken as probably, or Ux equal to Y. Maybe here, instead of the small x, we just use capital X, capital Y, from sympy, about symbol or symbols, X, Y, Z equal to NP array X, Y, Z. In fact, transpose. Sorry. So Ux equal to Y essentially means that I don't know whether dot will mark on this. Maybe you have to do. Okay, let me just try once. NP dot Ux. So this is what our Y is. Okay, capital Y is. So initial system is this X equal to B. Now this is what we have. Okay. So the next thing that we are trying to do, Ux is equal to Y. Okay, that's fine. So if Ux is equal to Y, the original equation actually becomes, see, remember that A is now Lu. So Ax equal to B now becomes Ax equal to B now becomes Lux equal to B. But now Ux we are calling it to be equal to Y. So Ly equal to B. Now, how do we solve for this Ly is equal to B? You can just try to see what this Ly is. NP dot Ly. This backslash n corresponds to new line. So go to the next line. That's what. Otherwise, Ly and this matrix will be printed on the same line. So Ly is this. Oh, that's not completely correct. Ly is equal to B. Ly is a lower triangle matrix, right? So what is L? So this is here L into there is something wrong. What is this? What is this U? Where this U is coming? U is 4 minus 2. So 4 into minus 2 into U and X. Okay, suppose that this is y1, y2. Okay, so we need to solve Ly is equal to b. Okay, what is this Ly? Just y1, y2. So let us call this as, suppose that we call this x to be equal to x. Okay, y is nothing but ux. And suppose now that y consists of y1, y2, y3. Okay, suppose now that y consists of y1, y2, y3. So in that case, y equal to the column matrix y1, y2, y3. So in such a situation, Ly is equal to b. Essentially mean that um, y1, y2, y3 we will be getting something. Okay, y1, y2, and y3 we are going to get something. Okay, let us just define instead of all these things, y1, y2, y3. Let me call. Let me define some symbols. Symbols y1, y2, y3, and let me just take Ly now. What is this? Instead of these things. Okay, let me just suppress this event. Capital Y equal to NP array y1, y2, y3 dot transpose. Now, if we try to see, so Ly is equal to b. So what is this Ly? Let us try to see Ly. Print np dot Ly. So y is already taken to be this. So let us see Ly. Okay, so this Ly is nothing but y1. So Ly is equal to b. Okay, we know that Ly is equal to b. So we are getting Ly to be 1 into y1, which is y1, minus 0.5 y1 into minus 0.5 y1 plus y2. That's the second entry. This is this. Now b is also known to us. Okay, see that b is also known to us. So how do you find y1 then? So we already have 1.0 y1. So that is y1. y1 itself is equal to b. Okay, because this is nothing but L21, right? So sorry, the first entry is nothing but 1.0 is nothing but L00. So to find y1, what do you need is, so it's always going to be like that, because the first entry we have decomposed in such a way that the lower triangular matrix will be having the diagonal entries equal to 1, 1, 1. So 1.0 y1, 1.0 y2, 1.0 y3 will be definitely appearing in these three equations. So for the first equation is going to be always y1. So y1 will be getting to be equal to always equal to that what you call y1 is going to be always equal to that first entry in the B matrix. Okay, y1 is always going to be equal to the first entry in the B matrix. y1 equal to first entry in the B matrix is B. How do we call that? 0, 0. Okay, how do we get y2? How do you get y2? So for getting y2, what do you need is you need um, to subtract. Okay, this is actually kind of okay. We should store these things into the y matrix itself. So y matrix, let us try to solve. So solving the y matrix, what do we need is this is the first entry in the y matrix. Therefore, let us take this to be capital Y 0, 0 instead of that. Once you find capital Y 0, 0, once you initialize this capital Y 0, 0 to be equal to this. So the first entry we are always initializing this to be this. Now to get the second entry, what do we need is from the second entry in the B matrix. Okay, so Y2 y second entry is nothing but 0 0 instead of that second. Okay, y 1 0. This is equal to, so what do we need from the second element in that B matrix, which is B 1 0. We need to subtract. What do we need to subtract? We need to subtract this particular entry. This is nothing but, remember that this is the lower triangular matrix and this 0.5 is, right? So this is nothing but minus L. Which entry is that? This is L. This entry corresponds to L10. So corresponding to Y10, you have L10 here. L10 star, whatever you have found. Okay, what you have found? L10, you have found this one, this element. Y1 is already there. So Y1 means this Y0. That's it. Now, what about the third entry? So the third entry is in that Y matrix is L20. L20 is going to be equal to what is it now you require? Y3 is nothing but Y3 is equal to, so from B3 you need to subtract. So B3 is here, B20 you need to subtract. So two things you need to subtract now. First is 0.5 times Y2. 0.5 is nothing but, once again, so this entry. Okay, this 0.5. And this you have to add. It will subtract only because you are going to remove it. So this is L20 Y. Which one you have to remove? Just 1 second. So Y3, the equation is that Y3 is equal to, from B3, you need to remove. So this is nothing but L31. L31 Y1 minus this entry is nothing but L32 times Y2. L32 Y2. So if you transform this into this, 31 is 20. Y1 is nothing but, Y1 means the very first element, which is this element, minus L32. L21 into Y. Which element we have computed here? Y10 we have computed here. Exactly the same thing we need to subtract. Y2 is nothing but the last element, which is Y. I think this should do. Let's try to see the Y matrix once again. Print Y. Y is here, 11 minus 10.5, 9.0. Okay, let me update the entire Google document once again. Update. So we have not completed only first part, only that Y we have found. In this Ly is equal to B, we have found Y. So now Ux is equal to Y. Now Ux is equal to Y. We need to solve for Ux is equal to Y. This is only for this. This was used only for demonstrating what's happening. Solving for Y. Ly equal to B for Y. Now on the other hand, we're going to solve Ux is equal to Y for X. So the next step we have to solve for Ux equal to Y. Okay, let us see what this ux is now. So ux is equal to y is what exactly? Let's try to see that. Print ux is equal to y. You require np dot product u x. This is what we want. So this is what essentially we want. Maybe we can make, let us put a new line. Now you can see that at the previous Ly is equal to b, we solved from the top. Okay, y1 we substituted into the expression for y2 for getting y2. Y2 we substituted for y1 and y2 we substituted for y3. So forward substitution. Here now in this case we need to do some backward substitution because we have 3z equal to 9. Okay, 3z equal to 9. Where remember that u is given to be where is the final u? U is given to be here, this entry. So 3z is here. So this is u33z. This is u33z. Okay, u33z is equal to 9. Therefore, z is nothing but um, that last entry x3 divided by u33. You will set it like that. So now the x matrix. The first entry is, maybe instead of doing all this, instead of transposing, maybe we can straight away take 1, 2, 3. That's also, instead of making it complex. Let us just take it to be equal to x equal to x, y, z, so that we can easily find it out. x0, x1, x2 instead of using double symbols, just for the sake of that. Otherwise, we need to again use double symbols. So the last entry is nothing but 3z. Okay, 3z is equal to 9. So z we are trying to find. Z is nothing but z is equal to the last entry in B is B20, B20. That's last entry. So B20 divided by U33. U33 is nothing but U22 in our, according to our notation. U22. Maybe we can print B. Print Z. Why is it happening like this? So 9, 3. U22. U B. What is it? Oh, sorry. You need to solve it for ux equal to y finally, not ux equal to b. That's a mistake. Okay. So therefore, you need y20 instead. Means that the 3. Now the next step is that we need to solve for y. Y is nothing but analogously. So how do we get y? Y is 3y minus 1.5z is equal to minus 10.5. So z is nothing but minus 1.5 z. Sorry, 3y we get to be equal to minus 10.5, which is y10. So let's take y10 minus. So this 3y we need to take. 3 is nothing but in the upper triangular matrix, 3 is this entry. So this is u11. U11 star. So what we have found, the value we set. Okay, let us find. Let's find that. Print y. Printing. So we get it to be minus 19.5. So y is found. Now the last one we are doing the backward substitution. So this is nothing but, so for getting the last value we need to take 4.0x. Okay, 4.0x. Okay, have we divided it? Oh, no, no, no. We need to. I think in the last step also we missed something, right? In previous step also we just we didn't divide it. So hello. I think someone is not muted. Okay, thank you. So in the last step also, I think we were missing something. So in this step, say that Ly is equal to b. We have taken y 0, 0. Okay, in that case, I think this was quite straightforward because diagonal entries were all one. So all the y1, y2, y3, we were getting it to be exactly like there were no coefficients with this y1, y2, y3 except one. So we were safe in that case. But in this case, it's not like that. In this case, here we are getting z is equal to y20 by u22. Therefore, you need to multiply. Just see this. So in this particular case, 3 points. So for finding y, we need this entry minus 10.5, which is y10 minus 3.0, sorry, minus 1.5 z. That is also done. Divided by this 3.0 is required. Okay. Star 1 by, or straight away 1 by 3.0 is nothing but, see that this 3.0 in u, this is coming 3.5, 1.5. Is it 3.5 and 1.5? 3 and 1.5. So 3 and 1.5, 3 is coming from here. So this 3 is nothing but u1 divided by u1. This is also required. So that's a mistake. So here in this case, once again we need to subtract from where? Subtract from y. So we are going backward. So 0, 0, subtracting. So two elements we need to subtract. What are the two elements? So we need to subtract 1.0 into z. We need to subtract. What is that 1.0? This is u 02. u02 z minus. What is the next thing that we need to subtract? u02 into z minus this entry you need to substitute. Minus this entry also we need to subtract. Minus 2.0 into y. This minus 2.0 is coming from here. So this is nothing but u 01 into y. Now we need to divide the entire thing, right? Divide the entire thing with the coefficient of x. The coefficient of x is what? That's 4.0. 4.0 is the first entry in the U matrix. So u 0, 0. Three minus 6.5, 1.25. Let's see if this is correct or not. At least the first one we can try to see. 4 star x minus 2 star y plus z. We are checking equality. Prime. Yes, true. So it says that it satisfies, the first equation is anyway satisfied. Checking the first equation satisfies, equation is satisfied. So let me update the entire program. So updated the complete program in the Google document. We need to actually do this in a loop instead of doing all these things. These steps. These steps actually can be done in a loop. But for that, the only thing is that you need to take z to be equal x to be equal to say x naught, x1, x2. We need to just take instead of taking z, y, x. Instead of that, we can just take here. We can take x3 or x2. Here x1, x naught. We'll try to do that. We'll try to do it in a loop after this. So the LU decomposition, you can just see that we have actually made use of the steps involved in the Gaussian elimination, and we are doing more operations comparatively, right? But the only important thing that we should remember is that, see, in the decomposition LU, we are not at all considering the right side matrix B. Okay, the right side column matrix B is not at all involved in computing the LU decomposition. So after, for solving only, we are making use of this B. So now suppose that, see, in the case of Gaussian elimination, it's not like that. We are solving the augmented matrix. So if our right hand side is changing, we need to repeat the entire operations one by one. But here, the advantage is that once you found this LU, then backward substitution is not that heavy. See, I'm talking about a situation where number of variables is much more comparatively. When we have only 3 variables, none of these methods are actually required. We can directly use our own, by our own hand. We can solve all these things, right? When you have a system of equations involving too many variables, and suppose that our coefficient matrix is the same, but we are changing the right side matrix. So performing the computation every times with the augmented matrix will become um, a lot of resource consuming, time consuming. If you have a large matrix, very large matrix, computation related to matrix is not that fast. Okay, remember that too many computations are involved. But suppose that you found this LU decomposition, then only backward substitution is actually involved in solving the system, corresponding to each and every B. So if you have only one system to solve, Gaussian elimination is much better. But if you have more system to solve, then you can save this LU decomposition somewhere, and you can make use of this LU for solving the other systems with different rights. That's the advantage of using the LU decomposition. Okay, now the next thing that we need to do is we need to automate this process. Here we have done this process of finding this y1, y2, y3. So in that process, we have these three steps. So since we have only three steps here, so solving manually is not very difficult. Okay, but suppose that we have four equations. Suppose that we have four equations, five equations, six equations. In that case, we may need to write this expression many times. Not only that, this expression actually becomes larger and larger, longer and longer, in fact. And here also it becomes longer and longer. So instead of doing this, we can try to, and here also, this also we can actually simplify. This also can be made into a loop. So let us see how to make use of loops for solving all these. Okay, after doing this, LU decomposition with loops. We will use loops everywhere so that size of the program will comparatively become lesser and understanding will be slightly better. Let me just copy and paste this to a new program. So this is the 65th LU decomposition. So this is the general version. Same matrix, everything exactly the same. No need to print A and B. We know that it definitely works. No need to print even L. So these operations. Now we need to take care of these operations. So what are the requirements here? See that here we have L10 equal to U10 U00. So initially we have this finding L10. After that we are taking U1. Okay, L1 U1. Now here L2 U2. Here you have L1, U1, U00, L2, U2, U00. So what is the recursive step in that case? So how many times do we need to go through this? Remember that the very first entry in the lower triangular matrix is actually 1. No need to compute that. So always we are starting with the second row first element. So for I in range second row, so which is 1. Second row to third row. Third row, remember that. So number of rows. Let us take even yesterday we have done that. What was that? Rows, columns. Okay. So let us take the rows, columns command once again, so that this will work for any dimensional square matrix. Call this to be R and C. And since this is a square matrix, both are going to be anyway the same. There is no difference. Now this is R, so that this can be generalized to any square matrix of any order. So that's it. Now I in range, where to where we have to go? Say that except the first element, we need to go till the end of till the last row we need to process. So the last row is now R, but R, okay, R is 3. Therefore, we require 1. So R is now 3. This is 3. So 1 is required, 2 is required. Okay, R is keeping R is enough. R plus 1 is not needed. So what is the step? This is I. This is also I. Now what is this step? Once again, this is I. This is also I. So this is when it becomes 2. That's it. So that is done in a loop. Here it is row I becomes row I minus this is again I. What after this? So in the second step, what you need to do? So second step, you need to go to the next row. Okay. So you forget about the second row. Second row is already converted. Second row, first element, you have already made it into. So the first, no, not actually, the first column has been made it into a column of the upper triangular matrix. Now you need to take care of the second column. Second column, first element. That's what you need. Second column, first element. You need to make the elements below that to be equal to 0. Okay. So for that, again, let us try to club these two things later. For I in range. So from where we have to start? We have to start from R. Sorry, 2. We try to simplify it. We try to simplify this. Exactly the same thing. So, but here it is not 0, here it is 1. Here it is not 0, here it is 1. Here it is not 0, here it is 1, 1, 1. Not 0, 1. This is correct now. U1, L21, L21, U2. It's fine. Now, how do we club these two? So these two are more or less the same thing, right? Li0, Ui0. Here Li1, Ui1. But remember that the 0 is changing to 1. That's the only difference. Zero is now changing to 1. So we need a second variable also, right? So in the first step, I is 1. So we are taking, so this is the ith variable. And this can actually be taken as the jth variable. Remember that the jth variable here, when I becomes, I is starting from 2. Okay, I is starting from 2. So we are taking this to be equal to 2. In the next step is I is equal to 3. We need to take this to be equal to 2. So what is the generalization that we can have here? Instead of writing this for loop multiple times, maybe we can have 2 for loops for j in range. From where we need to start? Here it is 0. Here it's 1. So okay, we just think Li1, Ui1. So we require 0 and 1 to be there. So essentially we are looking for okay, if there is one more step, suppose that there is one more step so that we can easily understand. Suppose that we have one more step here, what it would have been. So I in range 3 to R. Suppose that we have one more step. So it would have been 2 here. It would have been 2 here. What is this 1, 1? Okay, here it is nothing but, okay. So it would have been 2 here. It will be 2 here. I0, I think that's all the times that's going to be correct. So we have these 3. Okay, these 3 to compare. So 1 to r I0, 2 to r I1, 3 to r I2. So we need only that. So maybe we can take, remember that the range of I is, the starting element in the range of I is actually increasing. Okay. So we need to take a variable j outside in such a way that j is increasing from 1 to 3 in case we have r is equal to 4. Number of rows is 4. So up to r here we have to go here. So we need to put a variable like, okay, let me just do it here. For j in range. So from where to where I have to start, where to where I should go. 0 is essentially here. 0 to up to where? So I think up to r. So in this case, r is equal to 3. So we are getting 0 and 1. So 1 less we are getting. So r is 3. So we are getting not up to 2. So up to r minus 1. I think this is correct. Let's just see into this action. Now for I in range, so we need to start with j plus 1 because we are starting with this element j plus 1. Now this is j. Instead of 2 we have j here, j here, j here. I hope that this is correct. The 0, that's always 0, right? All the times it's 0, so we don't have to change that. This is it. I hope that this will give exactly the same answer. Okay, let me just see. Okay, this is not intended. Okay, I'm moving all these things. Trying to see if it's correct. Was not saved. So let me just remove the remaining part also. So is this correct compared to the previous thing? U is equal to this. L seems to be correct, but U, okay, let me just see. Where is that 64th program? What was the U previously? Oh, 4 minus 2, 1, 0, 3, 1 minus 1.5. 4 minus 2, 1, 0, 3. Okay, one second, once again. This is the previous program. Or not this one, this one. This is the previous program. And in this program, U is nothing but 4 minus 2, 1, 0, 3, 1 minus 1.5, 3. This is the previous program. Okay. So let me just move it here. And in this program, what's happening? Only the last elements are slightly, this should have been 0 and 3 instead. Right here we are getting, oh, but we are not getting upper triangle here. Okay, that's not complete therefore. So what's the problem here? Uij, Ujj, Uj. Okay, let me just compare this with the last line. So the last line should actually give us some hint. So what do we exactly need? In the last step, we require the last step. Okay, last step we require this. This is the final change. No, sorry. U2. This is the last step. This is the last step we have in the decomposition. So L21. So let us see what happens. R minus 1. R is now 3. Therefore, R is going up to 2 only. So 0, 1 only will go. So you will get u1. So now suppose that let us try to see in action what exactly is happening. So j is equal to the last element is now. So since there are three columns, three rows, so r is 3, therefore r minus 1 is 2. So it will go up to 0 and 1. It will go for 0 and 1. So j is the last value is 1. So last value is 1, therefore, so 2 to r. So 2 to 3, therefore only 2. So I is now 2, L2. J is 1. So U 2 1 by U 1 1. That's correct. Now U I is now 2. Oh, here it's L. This is equal to J. Okay, let us see if this is correct. This is correct now. 3. This is upper triangular anyway. So 4 minus 2, 1, 0, 3 minus 1.5, 0, 0, 3. Is this matching? 0, 0, 3 is okay. 0, 3 minus 1.5. I think this is matching. Yeah, seems to be correct. Now this is correct. So that's it. So the decomposition, see, the LU decomposition is only this much. Okay. So these two loops actually constitute the LU decomposition. That's completed. Now the only part remaining is that we need to solve for this backward substitution. For solving for this backward substitution, maybe instead of using this x to be equal to xy, is it okay? There is no problem. We can. We don't have to even use that. We may just we don't have to multiply anyway, right? So let us just take this x to be equal to xyz, which we are going to modify later. X, y, z. Just for showing the symbols, we are not using these symbols, but we need an array consisting of 3 elements so that we can replace. So y is here. Similarly, y also we can do like that. So this is not required. Y equal to, let us take y1, y2, y3 as a list. So this is not really necessary. This is also not necessary. Solving Ly is equal to b, that's fine. So instead of y0, 0, we can simply use y0. So instead of writing b0, 0, let us take b to b just equal to this. No need to even take it as an array. So only these values are important for us. So for showing it as a matrix, we are doing all these things. Otherwise, it's not necessary. So that our notation will be much more simplified. y0, y10, b1, L10 is required. Y0 again. So these are the steps that we need. B2, Y0, Y10 is not required. So let us see if it's Y10 is not required. So we need to change it even here. So this is Y1. Uh, 3 minus 6.5 minus 1.25. 3 minus 6.5 minus 1.25. That's correct. Okay, so now the thing is we need to convert this into a loop. So how do we do that? So we need to take, so this is nothing but if you are looping through 0, 1, 2. So essentially we require for I in range 0 to 2. 0 to 2 is, I think, since we have three variables, three equations, number of rows. 0, R. So what do we need from this equation? Probably we can understand what do we exactly need. So yi is nothing but bi minus sum of these two. Sum of what is that? So this is nothing but L I 0. Remember that L1 0, L2 0, and next is, so in the first step we require, so we need to subtract L2 0 Y 0 L2 1 Y 1. Okay, L2 0 Y 0 L2 1 Y 1. So L, okay, what do we require? L2 0 Y 0 L1. So from where to where we need to go? 1 and 2 we require. Y1 L0. One second. L21 L20 Y0 L21 Y1. So this 2 is actually I itself. Okay, Bi. So Li. So that's a fixed thing. So Yi is equal to, so now Li, this is 0 and this is 1. So let us take this to be equal to J star Y of J for J in. Now what are the J's here? Here it is 1 and 2. So here it is just 0. So here it is 1 and 0, or 0 and 1. Here it is 0 and 1, here it is just 0. So it depends on which one you are finding. If you are finding y2, you need 0 and 1. If you're finding y1, you need just 0. Okay. So it is from, so in range 0 to I. I think this is fine. Sum. Okay, let us try to see. Minus, yeah. Where is y? Y is 11 minus 10.5, 9.0. Let us see the previous step. Y is 11 minus 10.5, 9.0. Was it 9.0 here? 9.0. Yes, exactly the same. Now, for solving ux equal to y, exactly the same thing. So here, what do we need is, we are starting with z. So instead of z, we can call this as x2. So this is x1. So we require x2 here. We require we find x naught here. So this is x2. This is x1, and this is the final equation. So see that here we are making use of backward substitution, right? We are finding z first. So again the same thing. Let us look at the last thing. So here we need to start with maybe we can start with the 2. So we require 2 here. 2 to till where we should go? 2 to 0. Okay, 2 to 0 if you are going, it will be, we need to go in the reverse order, minus 1. So if you go, then that 0 may not be, okay, let us take 2 to minus 1. So that 2 will be included, 0 will, 1 will be included, 0 also will be included. With a decrement, not increment, we are decreasing with minus 1. And let us consider this, the last equation. So if you consider the last equation, what will happen? Last equation is nothing but, towards the end, we are getting xi equal to, so what is the step here? See that here we have y0 minus u0 to x2. Okay, if you are trying to find y0, so initially y0, in the next step we have, so this y0 is essentially here. So this is correct. Let us see. y naught minus u0 to y divided by u00. Here you require the division also. Here you are dividing with u11. So when you're trying to find xi, you are dividing with u00. Okay, that is found. So the last element is always going to be I. That is fixed. So what are the remaining things? Here you are subtracting from y1 u11 into x2. Okay. Here you are subtracting some y0 u02 into x2 minus u01 into x1. So from y0 you are subtracting here. So if you want to find xi from ya, you are subtracting. Okay. So yi, you are subtracting what? Ya minus. So u0 to x2, u01 x1. That is a sum. Sum of u, sorry, u0 to x2, u01 x1. That's varying. So u0 to u01, that 0 is fixed. J star x j. So 2 and 1 you should take if you're finding 0, or otherwise 1 and 2 you should take if you're finding 0. If you're finding 1, you should take only, see this. If you're finding 1, you should take only u11 x2. Oh, okay, there is a small difference here. This is u11 x2, u02 x2. This is correct. u11 x2 and u02 x2. Okay, let us just see. So division is essentially with that is correct. I. Okay, so u is missing here. This is perfect. There is no problem. But now, what are the things that we require? U0 to x2 and u01 x1. U0 to x2 and u01 x1. Here, u11 x2 and okay, that's a little bit confusing. U11 x2. u0 to x2, u01 x1. But how to call this? I think here you are the total sum is equal to 2. Can we say something like that? I plus j. So here you have I. Here you have 0 1. Okay, if you have one more, let us try to see if you have one more, what will happen. So suppose that you have one more in addition. So what you would have done? So instead of this, u0 to x2, u01 x1, probably u0. Okay, one more step you would have included. U03 x3, but that is only the last step. What about the previous steps? U0 to x2, u0 to x2. Okay, just 1 second. Let me just try to say that. X2 is equal to y is u0j xj uii. U0j, it's fine in this case. What about this case? Y2 by u22. N minus 1 minus 1. Okay, this is n minus 1 minus 1 minus 1. That's fine. Dot a k x1 by a k k. So whole divided by a k k. I think something is slightly missing here. Maybe we should just look at this particular part here. So what we did here exactly, we can try to see from here. So here x is equal to y00 u02 z. Suppose that we have x, y, z and one more variable, then we would have used y10 u11. What we would have done, y00 u02 u01. Maybe one more step had it been there. So in that case, so we will undo it. Suppose that we have some w also here, what we would have done. So y00. So in that case, we require the backward substitution to be, okay, let me just modify it slightly, just to see what's happening here. So in such a situation, we would have taken a w, x, y, z. So z is here, w is also here. So in such a situation, this would have been 3. This would have been 3, 3. So here, this would have been 2. 2, okay, sorry, 1, 1. Okay, this is correct. 2, 2, 2. Here also it's probably 2. Okay, in this case, 3, 0, this is 1, 0. Instead of 0, 2. That's the confusion. There is something slightly missing. I can just try to do that, but I think let me just update this Google document with this new program. I think we need to just look at the program with at least 4 variables. Then only we will be able to make it out clearly what exactly is going. There's the small problem here appearing is that programming is essentially nothing but finding the pattern so that we can implement it into a loop. So this last step, this one last step I am missing slightly. So maybe we'll be able to solve it quickly, but I don't know whether it will take more time or not. So anyway, let's just have a look at that. X0. So the only difference is this is not uniform. That's the problem here. So the pattern that we are following here is not appearing as a uniform thing. Here we have y2 by u22. Here we have, instead of that, y1 minus u11 into x2 by u11. Here we have y0 u02 x2. Here one more is increasing, u00. The next step I expect it to be y. If we have one more, so we need 2 more summations is what I understand. So u00. So in that case, we need to start this with u33, u11, u33, u22, u11, and coming down. So in such a situation, but such a situation, this particular combination is not going well. This is 0 to here. This is 0, 1 here. Here this is just 1, 1. But what could be the next possible thing? That's what I'm wondering. So u02. This is 0, 1. So here you have 1, 1. Here you have one extra thing. So okay, one more extra variable is required here, it seems, but where exactly that variable should be fit? Maybe here we need to take 0 here. This is 1 here, this is 0 here. So for finding 1, you need 1 here. So this is I. Maybe you require something like when j is increasing, the other part is decreasing. So here you probably require I. This is 0, this is 0, this is 1, this is 1. So 0, 2. Was it 0, 2 previously? Just see. This is 0, 2, this is 0, 1. But this is just 1, 1, 1. This is 0, 2, this is 0, 1. So everything is probably 1. Maybe the previous one is, if there were one more variable, it's 0, 3. This is 1, 1 again. So y is 1, 1. That's what I'm thinking. Why is this just 1 1? But the total sum is going to be equal to 2. Is it that the total sum has to start with 2? The total sum here we are starting with this is 1. But to understand that, we require some more time. Okay, I will do one. I'll try to do one thing. I will update the entire program in the Google Sheet, the link of which we have shared. Since I don't think that we have too much of time to spend on this problem, I think this is only one more step is remaining, only to find out what exactly we need to do in the case of 4 variables. If you write down the program for 4 variables, it should come out clearly, because now I am not able to exactly find out what's happening here. What that pattern I am unable to exactly locate in the 4 variable case. Okay, so probably with this I will, since today is the last session, I think I will probably stop with this. I will update the Google Sheet with the entire program, the remaining part of this program, and probably I will. Shall I just stop now, Anukumar sir?
Okay.
Yeah, the only thing is that the generalization of that LU decomposition is remaining. That the simpler case we have already found, the special case we have already solved. The generalization part only the last step. I believe that only the last step is remaining, and I can update that in the Google Sheet, the link of which I have already shared, maybe within a day. Okay, thank you very much. Up to here, I will update the Google Sheet already. It's already updated. Yeah.
So we can conclude this session now. I express my heartfelt gratitude to Professor Vishnu Nambudiri for the inspiring and motivating talk lectures on the workshop Python program. I also thank all the participants for the active participation. Now we would like to know the feedback from the participants. Anyone can volunteer. Please.
Good evening. My name is Anisha. I'm a research scholar in Department of Mathematics, University of Calicut. This workshop has been very inspiring, and I'm really feeling delighted to have been able to be a part of this workshop. We are lucky to have such an eminent person for our classes. We know that Python has become one of the most popular programming languages in the world in recent years. So I'm sure that this workshop provide a wide knowledge about Python for those who attended the classes. Uh, since Vishnu sir shared the Google document for all the programs, we can easily follow the classes. I really appreciate Vishnu sir for his effort to share his valuable knowledge with us. Thank you, sir, for this great classes.
Okay, thank you, Anisha.
Ma'am, I am Deepa Nair, Assistant Professor, Nursing Board, Pamba College, Parimala. And about our workshop, it was very well organized one. And it was really a good course on Python. I really express my sincere thanks to Professor Vishnu Nambudiri sir for the wonderful lecture. Sir has explained everything, each step very clear, and it was easy to understand. And almost all types of problems were discussed. And as a beginner, it helped me a lot, and I hope all of us have improved our skills. And it was such a very wonderful learning experience. Thank you very much, sir. And I take this opportunity to thank Dr. Raj ma'am, coordinator of this workshop, Dr. Anil Kumar sir, the organizing committee members. Once again, thank you very much, sir.
Okay, thank you, Deepa.
Good evening to one and all. Myself Shailajaji from Maharani Lakshmi Ammani College, Bangalore, Karnataka. I really felt the workshop was very much helpful because the sir started from basic and went slowly moved on to the advanced topics. So it really helped a lot. Even when we could not attend during the 2 hour session later on, his YouTube session was really helpful, sir. Thank you so much. And whatever the documents you shared with us, that also kept everything handy for us to work on. Though I know few things about the Python, but your Python started from basic that gave an insight to a lot of things that was missing. Thank you so much, sir, for giving us such a wonderful talk every day continuously. Thank you for your effort, and we have learned it. Thank you so much, sir, and thank you for the organization committee also. Thank you, everyone.
Okay, thank you, Ms. Shailaja.
Okay, good afternoon, all. Good late afternoon, all the present, the respected dignitaries present here. I am very much thankful to all the organizers, namely Dr. Anil Kumar B, Dr. Priti Kulkar, Dr. Sriniti, Dr. Prasad, and Dr. Mogen Nati for arranging such an excellent event. I am also thankful to Professor Raji for coordinating the entire session smoothly, and I am very indebted. I am very indebted to Professor Dr. K. Vishnu Nambutri for his tireless effort to make us understand every aspect of Python program in the last 16 days. I have never been such an I have never seen such an energetic person like Professor Vishnu. He is always humble to clear all the doubts that we have faced during this 15 days journey. And many cheers for the Department of Mathematics, Calicut University. Thank you. Good night.
Good evening, everyone. My name is Mohsina. I'm an MSc student of Department of Mathematics, Calicut University. It's been a great opportunity for us to participate in the 15-day Python workshop. A lot of thanks to Vishnu sir for spending your valuable time with us. As we all know, learning a new programming language like Python is a complicated task, but Vishnu sir has helped us to overcome that difficulties. For you explained each and every points very thoroughly and explained most of every aspects of Python. So you have made learning Python an easy task by your simple examples and step-to-step explanations. You made it easier to study for us by starting from the basic structure programs such as addition, subtraction, etc. It was very helpful for us that you shared every programs in Google document. It helped us to refer and clear our doubts very much. Also, thank you Department of Mathematics for organizing this workshop, and I personally thank Anil sir and Rajimis for coordinating such a wonderful workshop. Thank you.
Okay, Mohsina. Arya? Arya? Is there anyone to remaining to express their suggestions?
Good evening, all. It is. Hello, ma'am. Can you hear me?
Yes, yes.
I'm Sandra MS, first year MS Mathematics from Calicut University. It is time to conclude our Python workshop. Before coming to an end, I would like to thank Vishnu Nambudri sir for these wonderful lectures. It was really useful to each of us. Sir, your friendly approach made the whole session more interesting. Thank you, sir, for sharing your precious time and knowledge with us. This Python workshop was very helpful. It was very easy to do mathematics using Python after a few classes. Each day I was very excited to attend Python workshop because of the way you taught. Sharing the Google document was very different from other classes in the online platform. Altogether, it was a fruitful workshop. I thank our resource person, Vishnu sir, for taking the effort to make this workshop a success. I also thank our HOD, Anikumar sir, coordinator Dr. Raji Miss, for giving us the wonderful opportunity. I personally thank the Department of Mathematics, University of Calicut, for this amazing experience. Thank you.
Vignesh,
Good evening to one and all present here. First of all, I thank all for arranging such a good program because this is very useful for us for solving problem in computer programming. For UG, we have studied C and C++ program, but after that, this is a developed version, Python. But whenever we study the C and C++, it have a lot of complications. But after that, whenever we conclude the program, it may result in some of the many errors in the Windows screen. After compiling the program, we only know what the errors are. But in Python, it is too easy to find the earlier steps. It is too easy to avoid the problems. So whenever we have to go to learn the Python course, we only know how to run it on the computer and laptop only. But SAR says how to log in and it use in mobile phone and then all other devices accessible to us. So it is very useful to us to learn. Python is very interesting because he is started from the binary operations such as addition and subtraction. So from very simple level, primary level mathematics to very high level mathematics like limit, continuity, differentiability, like the topics also covered. So it is very useful for us. Above all, it is very useful. He has shared the Google document after the program is over, because listening the program and typing it in laptop and running it is very difficult task. This shows that Sir how understand the people who are the audience, how they are managed that. So it is very useful to us, sir. And I thank the math department for arranging such a very good program. Thank you all.
any more suggestions from the participants? Remarks?
Good afternoon. I am Stage B of here. It was really a good course. This course helped me gain deeper insight in Python.
I think the signal from his side is very weak.
Good. Explanations were clear to us. And I thank the for giving us the opportunity to attend this course.
Anyone want to tell more about the program? Now I invite Dr. A.P. Vinesh to deliver what are things.
Ma'am, am I audible?
Yes. Yes, you are.
Am I audible?
Yes.
A warm good evening to one and all. Let me propose vote of thanks to our 14 days workshop on Python program organized by the Department of Mathematics, University of Calicut. I am immensely honored to be a part of this program. As we all know, Dr. Vishnu Nambudiri has inspired and enlightened the attendees simultaneously with his erudite lectures throughout the entire course of the program. In the introductory part, Dr. Vishnu Nambudiri discussed fundamentals of Python programming, such as how to getting it, installing it, and running it. Then he proceeded to various mathematical concepts and related problems, such as maxima-minima problems, factorization problems, limits and continuity, derivatives, applications of derivatives such as area between curves, length of curves, etc. Linear algebra was one of the important areas discussed among the various significant concepts. Obviously, all the participants have enjoyed all these sessions. Thank you, sir. On behalf of the entire mathematics fraternity, let me thank Dr. Vishnu Nambudiri for enriching our program with his scholarly lecture. Next, I would like to express my sincere gratitude to Professor Dr. V. Anil Kumar, Head of the Department of Mathematics, University of Calicut, for being the constellation for the workshop. Now, let me thank the coordinator, Professor Dr. Raisi Pilakat, without whom this wouldn't have been possible. Now, I would like to thank the other organizing committee members, Dr. Priti Kutipulapur, Dr. Sinipi, Dr. Prasad T, Dr. Mupina T, for effectively executing this program. Last but not least, let me thank all the participants and attendees who have made our program a grand success. Thank you all once again. Thank you.
Now I think we can wind up. Thank you all once again. Good night.
Thank you, ma'am. Thank you all. See you.
Thank you.